in a counter flow, right? So these terms are very important, right? In a counter flow, double pipe heat exchanger, right? Water is heated from 20 degrees Celsius to 60 degrees Celsius, right? That's very important. Buy an oil with specific heat capacity of 1.45 kilojoules per kilograms per kelvins at a mass flow rate of 0.9 kilograms per second. The oil is cooled from 220 degrees Celsius to 150 degrees Celsius, right? Okay. And the overall heat transfer coefficient of the heat exchanger, right? HE means the heat exchanger, right? Is 400 watts per meter squared per degree Celsius, right? So that's a problem, right? So we have to calculate these four things, right? Rate of heat transfer, mass flow rate of water, and surface area of the heat exchanger. All right. Then surface area of the heat exchanger if the flow is parallel, right? Because now in the original problem the flow is actually counter flow, right? So now let's make a sketch. All right. Right. So let's make a sketch. Now first of all, here we need to identify what are the two types of fluids, right? From one side we have the hot fluid, right? And from the other side we have the cold. Alright, so now the first thing is that we have to clearly identify the two types of fluids, right? Because from one side we have the hot fluid, right? And from the other side we have the cold fluid, right? So first of all, I will make a simple layout, right? So now this is our heat exchanger, right? So just a simple layout, right? So this is our, what is this is the shell, right? The shell like thing, right? And from this side we have the tube. Alright. Alright. So let's say the hot fluid enters from the right end, right? So from this side we have the hot fluid. Alright. Because this inlet is that is where the hot fluid enters. Alright. So temperature is 220 degrees Celsius, right? So now the hot fluid enters like that. Okay, right? So now the hot fluid enters like that, right? And the hot fluid exits from here, right? So let's say T hot out, right? So these are our notations, right? T hot out, right? What is this one? T hot in, right? THI. T hot out. All right. And from this side we have the cold fluid inlet, right? T cool inlet, right? So now the cold fluid enters like that and it exits from here, right? T cold out. All right. Because now you can very clearly observe, if I am going to consider the direction of these two flows, right? The directions are actually opposite, right? The directions are opposite to each other, right? All right. So now our flow is counter flow type, and this is the simple layout that we need. and also at the same time we'll sketch the temperature profile also. All right, now this is the temperature T, right, and this is the, let's say, length of the heat exchanger, right, from the inlet, right. And here in this type you clearly observe, right, the inlet of the, or the inlet for the hot fluid and cold fluid are not at the same side, right, because at the right side we have the inlet of the hot fluid, and in the opposite side, or in other words on the left side, we have the inlet for the cold fluid, right. So now if you are going to set the temperature profile, all right, some dotted line, right, this is how the temperature varies for the hot fluid, right. So I'll just make the direction like that, right. So what is the starting temperature of the hot fluid? 220 degrees Celsius, and it ends at 150 degrees Celsius, right? Because in the problem it clearly mentions 220 to 150, right? The temperature variation of the hot fluid, right? And what about the cold fluid? The cold fluid enters at 20, alright. Right? This is 20 degrees Celsius for the cold fluid. And it's now, if I were to consider the hot fluid, this is the direction, right? I'll erase this part, right? And this is for the cold fluid, right? You can observe the directions are actually opposite, right? So 20 degrees Celsius to 60 degrees Celsius, right? All right. So now that is clear. Yes. So now, all right. So now let's begin, right? And we know that when solving this type of problems, right, actually the heat released by the hot fluid, right, so that equals to the heat gained by the cold fluid, right. So let's better write that, right. Heat released by the hot fluid, right, heat released by the hot fluid, right, that equals to the heat gained by the cold fluid. Alright, so that's the logic. So the first part is to calculate the rate of heat transfer, right? Yes. So based on the given information, right? Alright, consider the cold fluid. Alright, what is the equation you can use? Q dot for cold fluid equals mass flow rate and specific heat capacity of the respected fluid into the temperature difference, right, delta T. So what is the mass flow rate of the cold fluid? No. So we cannot use this equation. Why? Because in the second part it asks the mass flow rate of the water. Alright? Because in this problem oil is the hot fluid, right? Oil is the hot fluid, right? Then water is the cold fluid. Alright? So when calculating the heat transferred, we cannot consider the cold fluid. What is the reason? Because we don't have enough data, right? So let's consider the hot fluid here. Consider the hot fluid, right? Because if we consider the cold fluid, we don't know the mass flow rate, right? So Q dot equals, right, mass flow rate of the hot fluid into specific heat capacity of the hot fluid. Let's say CPH, right? Specific heat capacity of the hot fluid, right, into delta T, temperature difference. So what is the mass flow rate of the hot fluid, right? It mentions at a mass flow rate of 0.9 kilograms per second. 0.9 is the mass flow rate of the hot fluid, right? What is the specific heat capacity of the hot fluid? 1.45. I'll better write with the units, right? That is very important. This is kilograms per second. 1.45 kilojoules per kilograms per Kelvin, right? Isn't it? Yeah. Temperature difference doesn't matter whether it is a Kelvin difference or Celsius difference, right? 220 minus 150. Now carefully observe, kilogram to kilogram you can cancel, right? Kelvin to Celsius, degree Celsius, I mean like the temperature difference in degree Celsius, that also we can cancel, right? So we have kilojoules and we have seconds, right? So kilojoules per second, that is something similar to what? Kilojoules per second value, that is similar to a value in kilowatts. Is that clear? Right? So then let's carefully do the simplifications. Alright, so what do we have? 0.9, 1.45, 220 minus 50. So that means 70, right? The difference is how much? 70. 91.35. 91.35 kilowatts, right? So this is the rate of heat transfer, right? That means the rate at which the heat is released, right? The rate at which the heat is released by what? Hot fluid, right? So it is 91.35 kilowatts. So what is the answer to the first part? So answer to the first part is 91.35 in kilowatts, right? So that is the answer to the first part. So let's better write these values at somewhere else because I need space, right? Right. So 91.35 kilowatts is the answer to the first part, right? Okay. So now let's consider the second part. All right. I hope that is clear, right? So now students, I will erase this part, right? Because I need some space, right? And also when you are solving this type of problems, be very careful about the units, right? All right. Now, what is the second part? Mass flow rate of water, right? So now actually we know that water is the cold fluid here, right? So we know that Q heat, the rate of heat that is released by the hot fluid is that equals to the rate of heat gained by the cold fluid, right? That means water, right? Now we already know what is the rate of heat transferred for the hot fluid, that is 91.35 kilowatts, right? So let's say the mass flow rate of cooling water is, let's say, MW, cooling water, in other words water, right? This is the mass flow rate of water. Alright, what is the specific heat capacity of water? Let's say specific heat capacity of water, or in other words, specific heat capacity of Cp, let's say C. Now this C stands for the cold fluid, right? Times the temperature difference. MW, this is the thing that actually we need to find because we don't know that. What is the specific capacity for water? 4.184, right? So 4.184 kilojoules per kilograms per Kelvin. Temperature difference 20 is the inlet, 60 is the outlet. So 60 minus 20. This is 91.35 in kilowatts, right? So definitely, if you carefully do the simplifications, MW dot, what will be the unit? Definitely the unit must be kilograms per second, right? Alright. So now let's do the simplifications, right? 91.35, right? 91.35 and divide that by 4.184 and divide that by the temperature difference 60 minus 20, that is 40. Alright. Yes, so what is the answer? I am getting 0.5458. 0.5458. 0.5458. So let's round that value and keep 0.546, right? We can round for the third decimal, right? 0.546 kilograms per second. That is the mass flow rate of water. And I hope that is clear. Alright? So let's write that answer here because I need space. 0.546 kilograms per second, right? Yes, that is the answer for the second part, right? So now I will erase this part, alright? Now, yes, now surface area of the heat exchanger, right? So now, what are the equation we need when considering the heat exchanger? The rate of heat transfer Q dot of the heat exchanger, the rate of heat transfer Q dot of the heat exchanger, that equals the overall heat transfer coefficient U times the area of the heat exchanger times the logarithmic mean temperature difference, LMTD, right? So now what is the target? So now the target is we need to find what is LMTD. So let's find what is LMTD. So what is LMTD? LMTD equals delta T1 minus delta T2 divided by ln delta T1 divided by delta T2, right? This is the equation. So now let's see how can we find delta T1. Delta T1 equals what? T hot fluid inlet temperature minus T cold fluid outlet temperature. What is the hot fluid inlet temperature? That is 220 degrees Celsius minus cold fluid outlet temperature is how much? That is 60. Right? So 220 minus 60. What is the value? 160 degrees of Celsius. What is delta T2? T hot fluid outlet temperature minus T cold fluid inlet temperature. What is the hot fluid outlet temperature? 150. Minus what is the cold fluid inlet temperature? That is 20. So 130 degree Celsius, right? And I hope that part is clear. So now how to find LMTD? 160 minus 130 divided by ln 160 divided by 130. What is the answer? ln, so let's say 160 minus 130, right? Divided by ln 160 divided by 130. So I am getting the answer for the LMTD, the logarithmic mean temperature difference, as 144 144.48 degrees Celsius, right? 144.48 degrees Celsius, right? So that is the answer for LMTD, right? So now we know our value for LMTD is this much, so I need some space, right? So shall I erase this part, right? So I erase this part, right? Alright, so I'll keep this part because I need the value, right? So now this is the heat transfer rate for the heat exchanger, right? This is the overall heat transfer coefficient for the heat exchanger, and this is the area of the heat exchanger. This is LMTD, the one that we have calculated here, right? So what we need to find is the area of the heat exchanger, right? So what is the rate of heat transfer? So that is same as what we have previously calculated, whether it is the heat that is given, heat or heat that is released by the hot fluid, or the heat that is gained by the cold fluid, right? So we know that Q dot HE, I mean like the heat transfer rate of the heat exchanger is how much? So that is 91.35. So alright, it is 91.35 units kilowatts, right? So better write with the respective units, so that is better, right? And be very careful, what is the overall heat transfer coefficient of the heat exchanger? That is 400 watts per meter square per degree Celsius, right? But here this value is in kilowatts, but this value is in watts, right? Be very careful, so better keep that value in kilowatts, or you can convert this kilowatt value into watts, right? But what I will do is I will convert this, the value that is given in watts, into kilowatts per meter square per degree Celsius, right? So what is given is 400 watts per meter square per degree Celsius. So that 400, if I divide that by 1000, what? So that will be kilowatts per meter square per degree Celsius. Is that clear? Right. So now we have the area, right? And we have LMTD. What is that? 144.48. That is in degree Celsius, right? Because I wrote the units for your betterment. Alright. So now if you carefully do the simplifications, right? 91.35 kilowatts, 400 divided by 1000 multiplied by the area into LMTD value 144.48. So definitely the area we will get in terms of what? Meter squared, right? So let's do that. 91.35. So this value, let's divide by this one. Divide that by 144.48. So area I am getting as 1.58, right? Yes, 1.58 meter square, right? So surface area of the heat exchanger is 1.58 meter square, right? 1.58 meter square, right? So yes. Alright, so now the next part, right? What is the next part? So the next part is surface area of the heat exchanger if the flow is what? Parallel, right? So how can we solve this type of a problem, right? Yes, let me teach you how to do that, right? Alright, because now we have to find the surface area considering the flow is parallel, right? So now I will erase this diagram, right? Because I need to sketch a new layout. Alright, alright. Okay. Fine. Now, in the next case, we have the parallel flow. Right. So this is the tube with the shell, right? So now let's say the hot fluid enters from here, right? So let's say the hot fluid enters from here, right? So T hot out. Is that clear, right? This side T hot in, right? T hot in, right? The entry of the hot fluid 220 degrees Celsius, here 150 degrees Celsius, right? And the cold fluid enters from here, T cold inlet. Now you can see, if I am going to observe the two directions, right, of the two flows, T cooled out, right? Now here in this case, if I am going to consider the directions of the two fluids, right, you can observe it is the same direction, right? Same direction, right? So now the profile T hot inlet 220 degrees Celsius, right? So I can erase this part. So now let's get the temperature length profile, right? The length of the heat exchanger, right? So now what about the hot fluid? 220 degrees Celsius, 150 degrees Celsius, right? And what about the cold fluid? So that will be like this, same direction, 20 degrees Celsius to 60 degrees Celsius, right? Alright, here we have the decreasing curve and here we have the increasing curve, right? Alright, so now here we have the respected temperature profile, right? Because now we are going to consider the parallel flow, right? Now, how can we calculate LMTD? Now the target is LMTD, right? Alright, so now what is LMTD? Logarithmic mean temperature difference. Logarithmic mean temperature difference is delta T1 minus delta T2 divided by ln delta T1 divided by delta T2, right? So here what is delta T1? Delta T1 is T hot fluid inlet, right? T hot fluid inlet minus T cold fluid inlet. Because you know, previously when we were calculating this one, it was T hot fluid inlet minus T cold fluid outlet previously, right? So here it is T hot fluid inlet minus T cold fluid inlet. What is that? What is the T hot fluid inlet? That is 220. What is the hot fluid inlet? Is 220. What is the cold fluid inlet? It's 20. So 200 degrees Celsius, right? So 220 minus 20, 200 degrees Celsius, right? So what is delta T2? That is T hot fluid outlet minus T cold fluid outlet. Hot fluid outlet minus T cold fluid outlet. What is that? 150 for the hot fluid minus 60. 150 minus 60, how much? 90 degrees of Celsius. So now LMTD is how much? 200 minus 90 divided by ln 200 divided by, and ln of 200 divided by 90. What is the answer? Ln 200 minus 90, alright, divided by ln 200 divided by 90. So LMTD value is 137.75 degrees Celsius. 137.75 degrees Celsius, right? Actually it was 137.756. So better say it was actually 756 degrees Celsius, right? So better round that for 2 decimals. Better say 137.76 degrees Celsius. So that answer is better. Better LMTD. 137.76, right? So now we know the value for LMTD, right? So I will erase this part. So now I need to find what is the area. Alright. So we know heat transfer rate for the heat exchange equals overall heat transfer coefficient times area times LMTD, right? So then what is area? Area equals Q dot, alright, divided by overall heat transfer coefficient LMTD, right? You better subject area, that equals Q dot divided by U times LMTD, right? So how can we find the area? Q dot you already know, that is 91.35. 91.35 is Q dot. What is the overall heat transfer coefficient? That is 400. So better write it as 400 divided by 1000, right? For the unit conversion, right? LMTD how much? 137.76. So what is the answer? 91.35, right? Divided by so the area I am getting as 1.657. 1.657, so better say 1.66 meters squared. So what has happened to the area? 1.66. So the area has been increased, right? Because previously it was 1.58 meters squared for the counterflow, and now it is 1.66, right? So the area has been increased, right? Yes. So this is how we are going to solve this type of a problem, right? And I hope everything is clear. If you have any doubt, any problem, you can comment, right? Yes. Thank you very much and best of luck for your upcoming exams.